So today is a topic that I really like a lot. I've been holding off on it because I think that we now kind of have some more context for how generative models work, even though they're still quite opaque. I think that we've explored latent image generation and maybe got to some grappling of how a generative model can basically just take a pile of numbers and then spit out something like an image. And we're going to extend that idea into text generation today. But we're going to start with a bit of context and bring us to modern day by the end of this context session. And then we'll jump into hands-on coding. Okay, I'll just get started then. So I want to just kind of, I'm not saying that this is comprehensive by any means, but I want us to just like have some markers in time that, for me at least, really seem relevant to present day computational arts practices with text. And if you find that this becomes part of your own practice, each one of these slides, I think, are further places of investigation that you could dig further into and find more context for your practice or ideas or inspiration, as the previous lecture slides, I think, have been. But I don't know if I've made that very clear before, so doing that now. So starting with music erratum, I'm probably saying the name of this piece wrong. Does anyone know what this piece is? Okay, erratum musical was a piece in 1913. Duchamp playing with the idea of chance in the composition of music. And it's sometimes talked about as like the first chance process of music that had been composed. I'm sure there's many others, but at least from a Western narrative, in the art circles, this was one of the first, and then it was performed as well. And kind of in that ethos and era, there was the Dadaists playing with these ideas, and Duchamp went on to heavily inspire people in the 40s, 50s, people like John Cage and Alison Knowles, who also explored chance operations in their music as well as in text processes. So this is a pretty seminal marker, I find. And there's a lot more out there with Duchamp in terms of chance operations, and just the idea of process starting to become part of artists' own process, like thinking about chance processes or mechanical processes or things that could be computed and codified. Those sort of things start to happen much more and more in the start of the 20th century. And hand in hand, there are things happening in the science realm, in engineering, in warfare and cryptography, and all these things are influencing everybody every which way, and artists are exploring those processes in ways that we now can contextualize and think about 100 years later in such an interesting way, I think. So it's really fascinating. This arc of computation is really fascinating to me. I mentioned Tristan Tzara in the first class as well, and thinking about this two or three things out of this. So there was the kind of first idea of cut up was this Dadaist poem Recipe by Tristan Tzara, and he had famously performed this by like having a hat and like all these cut up pieces of paper, and was just like collaging one phrase to the next. And it seems so dumb now, but like at that time, I guess it was very novel idea that that could become part of a performance, and introducing chance and cut up in that way. And then there was also this parlor game, Exquisite Corpse, which you have probably played at some point in your life, or seen, which is quite fun. And that was a surrealist game. Okay, so cybernetics. I mean, I could have a whole course on this topic. It's really deeply fascinating. I'm just kind of including it here as a slide because it intersects with what's happening in between the 20s and what we just talked about with the Dadaists and Surrealists, and what is coming up, which is, you know, actually a lot more computational driven. And so you have Norbert Weiner and Claude Shannon and many other people involved in you know, the Manhattan Project and developing an atomic bomb as effectively, as well as working on Second World War encryption and decryption of enemy communications. And all this stuff is happening in the computing realm, trying to understand, like, how do I encode my transmission in a way that the enemies won't be able to decipher it? Or how do I decode that transmission and find out what they were communicating? And it started off this whole slew of ideas in terms of like feedback and systems communication, which 10 to 20 years later grew into systems theory. It grew into ecology. So ecology was an extension of cybernetics. And then you have all this philosophy of mind stuff starting to grow, like the way that people start thinking about what mind entails. Like in the 60s, people thought that B.F. Skinner was like a predominant narrative of mind, and he was a behaviorist. He thought that effectively we could be described by sensorial signals like a reptile might be. But things started to change very quickly after, when people started to realize that there were processes all around us, that we couldn't just be described as a brain in a vat. We had to move, and there are things happening around us, and we're social beings, and a lot more information than just what's happening in our brains. Like there's information everywhere constantly. And this was like one of the seminal texts that really kind of unleashed these ideas. And around the same time, so this was like 1942 or something like this, William Ross Ashby worked on this homeostat, which was sometimes cited as like the first cybernetic artwork. And it had these kind of like 4 bomb encasings that were all responding to each other and in homeostasis, and some sort of very kind of what's the word, like an equilibrium state, right? So they're all dependent on each other's sense actuations, but they're able to sense them and at the same time actuate themselves. And so there's this really kind of middle ground of when things aren't exploding, basically. Quite a cool work. Definitely dig into that if that interests you. And, you know, yeah, like how else to describe this? But around this time in the 40s, you know, there are a lot of these developments in computation come from ideas in physics. And so you will see things like Hamiltonian dynamics or thermodynamic laws that come like this piece, talking about what it means to be in equilibrium, and talking about temperature as a constant or as a factor that describes, you know, when that system is in equilibrium or not. And we'll come back to this idea of temperature in text generation, strangely. So if you've already come across it, maybe you're familiar with it, but when we'll work with text generation, that same idea of temperature as it is described in thermodynamics is actually used in the control of a generative text engine. So keep that in mind. We'll come back to it. So 1951, now we've got John Cage, having been inspired by Duchamp. At the time, you have pianist David Tudor, you have Duchamp around, you have Alison Knowles, like all of this stuff is happening within music now in terms of chance operations. And this was also quite a cool piece. And they had been heavily inspired by Li Xing, and other artists as well had been similarly inspired by that. Yeah, I mean, there are threads here, basically. I won't go too deep into these. Then you have Eliza. I forget what year this is. This was maybe early 60s, I forget. Where you have a psychotherapist as a chatbot, effectively. Oh, it says here, 1966. And so this was an implementation by this person here in 2005, and you can find this online as web apps, things like that. But quite cool, even then in 66, they were thinking about how text generation could be used to simulate entire conversations with people. And this idea of psychotherapy is really predominant in natural language processing, because often the task is to recognize sentiment. Are you being hostile? Are you positive? What's your emotion valence state? And there's a lot of really interesting types of natural language processing or computational processing of language examples which play with this idea of like they act as therapy agents in some way. Alison Knowles, who was at CalArts for a time, worked with James Tenney. Pictured here is Duchamp and Alison Knowles. And she worked with James Tenney on this piece, House of Dust, which used, and this was like 66 or something as well, like quite early. And this was a generative text that was a poem that had different rules that were written in this language of prologue. So it's not like a neural network type of artificial intelligence, but it was a more rule-based artificial intelligence. And this was a really cool piece. And I don't know if anyone has seen any of the performances during the Fluxus series in LA last year, or 2 years ago now, but this was performed quite a bit in LA. Cybernetic Serendipity is one of the first large exhibitions of cybernetic art, of which Alison Knowles presented House of Dust as well. Lots of really cool work here. This is a melting pot of really crazy stuff happening. I wish I could have seen it somehow. Okay, so 1980s, you have this really popular science text by Douglas Hofstadter, writing about these 3 different people: Gödel, mathematician; Escher, of course, the painter, or is that what we call it, a painter; and Bach, the musician, composer. And just a fairly inspiring piece of work. And within this text, he had also written a generative text language, and that went on to inspire a lot of people as well. So there's a lot in that book, but that was a rule-based AI. Okay, I'm like really hopping forward very quickly. Like there's loads and loads of stuff in all of these decades, but these are just the ones that I'm picking out. The postmodern generator, 2005, no, sorry, 1996. Oh my God. So 1996 was the postmodern generator. If you go to this link, you will see what it's all about if you haven't seen this. Okay, so this is the paper. The reality of genre, semantic subtextual theory in the works of spelling. So what is that? In the works of spelling, a predominant concept is the concept of neo-dialectic culture. In a sense, in Beverly Hills 90210, spelling affirms capitalist materialism, and so on and so on. So what is this? This is a generative algorithm that will generate more and more postmodern texts. And it's really fun, works quite well, doesn't need a neural network. It uses, I believe it uses Markov models. And Markov models go back to the 40s, which were used to model stochasticity and also aided in the development of the atomic bomb. So there you go, from the atomic bomb to the postmodern generator. Let's see. So yeah, and they mentioned they were also inspired by Douglas Hofstadter. Cool, so now 2007, we've got Watson on Jeopardy. Watson is performing speech recognition as well as natural language generation and then speech synthesis. It's got this crazy knowledge base. It's consumed most of Wikipedia, and it goes on to Jeopardy and does a great job. After Jeopardy, they decide that they should train Watson on the Urban Dictionary, which lands it in some trouble and in the news, and it swears and does a lot of things that it probably shouldn't as an AI representing a major corporation. Microsoft decides to try not really learning from the mistakes of Watson in 2016, and they tried to blacklist certain topics, which I think there's must be a better word than blacklisting, like you know, having a different list of words basically that that algorithm shouldn't be using, and they were taken offline, even though they had a similar service developed by Microsoft in 2014. So 2 to 3 years, they had already been running a generative text bot, like a chat bot, and didn't get in trouble during that time somehow. They were quickly taken offline in the US though. So check out Tay. 2016, so YouTube wasn't working yesterday. I hope it's working now. I don't know if anyone else noticed that. It was just me. This is the wrong link. Okay. Has anyone come across Sunspring? Feel free to unmute and talk to me. I'm here. If you'd like. So Sunspring was a film developed by Oscar Sharp, the algorithm, or directed by Oscar Sharp, and then Ross Goodwin was the creative technologist who trained a model on different screenplays and then had it generated this new script that they then curated and turned into a short film. And at the time, it was, you know, it was super weird. It was just very, very weird. And features Thomas Middleditch. So you can watch a short bit of it. This is the generated script, and then they generated some song lyrics. And then they asked these actors to go and make the film, like go and figure out how to act it, you know, with direction by Oscar Sharp.
In a future with mass unemployment, young people are forced to sell blood. It's something I can do.
You should shoot a boy and shut up. I was the one who was going to be 100 years old.
I saw him again. The way you were sent to me, that was a big, honest idea.
So, I mean, I think it's incredibly fun. It's like super incomprehensible. And I think the actors did a great job trying to extract meaning out of it and just had fun with it. Yeah, it's really interesting. And so this algorithm, which we're going to look at, this exact same algorithm that Ross was using here, this algorithm generates one letter at a time. And so it has some internal state, which is just a set of numbers. And as output, at each step, it's going to output a probability distribution over every possible letter that it was trained on. So let's say 27 letters. It'll output A to Z, and it'll say for A to Z some probability for every letter, and maybe the highest probability letter was A with like a 0.2. And so it'll output an A, and if it goes and outputs that A, it changes its state as a result of that output. Because we can then feed that A back into that model and say, you just output an A, update your internal dynamics to now change what your numbers were, and now you are in a new part of your latent network space. So if you try to visualize this and conceptualize what this model is doing, it's like the StyleGAN latent explorer in a lot of ways. You're hopping around different parts of this really high dimensional space. And that high dimensional space for an image model represents images, whereas for a model that does text generation, it represents something sequential about language. So it's hard to visualize into something like a latent space explorer, but the way that I think about it is more like it's a dynamical system. So it's like a latent space explorer that changes with time. And you imagine that each part of this space is a letter, effectively, with like more distribution to certain letters than others. We'll come back to that. Ross Goodwin, again, looking at, he went cross country and had like strapped a camera to his roof, I believe. He did that on this work. Yeah, and so he was taking photos and generating images from the photos, and he compiled a text of all generative text. I should know more about this. I feel like he applied some algorithms on the images to then generate the text, but I could be totally wrong about that. Anyway, look it up. It was quite cool. Yeah. This one I have to throw in there because I was involved. It's probably not that interesting, but I figure why not. So this was a generative, this was a topic with the mathematician Marcus du Sautoy, and I worked with Robert Thomas on this to develop generative music, which we then asked the audience to try and decipher. It was fun, it was cool. There's some documentation online. Check it out if you want. S. Devlin, who I mentioned on Tuesday, really, really amazing artist. She had some work in the LA Phil recently, or what, like 2 years ago or a year ago. Maybe you saw it. She does quite impressive stage design and theater pieces and like very immersive, large scale works. She's working on the, here she's in Trafalgar Square in London, and works with the team of people to project generative text on the lion in Trafalgar Square, as well as on the column there. And this work also existed online, so you could interact with it via a website. And in her language, you could donate a word to it, and it would then be used as part of the generation of the text of this piece. She has other work in this vein, in terms of, and technically in this vein, but quite different otherwise in terms of installation and aesthetics and everything. The other one I'm thinking of is poem portraits, which I can't find. Maybe. No, this is yet another one that's using the same underlying technology. The idea with all of these works is that there is a text generation backend, and there's a seed text, which just means that we're going to give this text generation algorithm a couple words that we've already determined what they are. And then you, as a user of this artwork, let's say, as somebody who's interacting with this artwork, you can further seed that model with more text, like help. You know, I want to feed the word help to that line and then see what comes out. And then I will see the rest of the generation as a projection, or as snippets of words here, or in the other case, I'll just look this up. Yeah, in the other case, you'll see it as a generation of text on somebody's face. So if I try and use this, I'll donate a word. These are all generated text phrases. So I'll write the word help. I will donate. And I'll give them access for my face. Okay, this is my phone. Okay, saying something, hello. Oh, I should click a button. Okay. This is too close. So it's detecting the depth in the image that aligns to my face. It's got like a whole model of the face, and then it's generating the text based on that word that I had given it. And it will show the generated text here as well as on my face. And she had this set up as an installation as well on the Barbican. It was quite cool. Okay, any questions? Feel free to jump out if there are. Alison Parrish, she's been working in New York and has definitely advanced computational poetry in a way that like very few people have. She's very intimate with the tools that she works with and is training models and working in like very open source ways, and also teaches quite heavily in NYU's ITP program. And I think a lot of her materials are online and freely available. Really, really cool work. Definitely dig into what she's up to. It's really quite different than anything else that we've looked at in this lecture so far. She often plays with the idea of like nonsense and exploring language's bounds and how to use these computational models to play with rhythm and sounds of words and things like that, which are often really quite fun. Okay. And then as a kind of another example, we have the AI dungeon. So this is a choose your own adventure generative text adventure. So you can pick a setting, and you can imagine that this is effectively, again, setting something like a seed for a generative model. So there could be a generative model trained on a lot of different things, and then you, by picking one of these settings, you're saying to this generative model, you know, read a bit of text about mysteries so that you get your headspace into that world. Much like in the same way that with the StyleGAN Explorer, you're saying like, oh, I want all images of like redwood trees, to use Tuesday's examples. Like if I'm trying to find more images like redwood trees, I'm going to go to that part of my latent space. So that's what's happening here, is like we're going to tell the model, I want to be in that part of generative, in that part of your generative world. So let's go to Cyberpunk, Android. We'll enter character's name. I mean, if I could type, I would. Let's see, down here. Okay. What should the name be? Okay. Let's just do Spot. Fine. What do you do? You're given the choice of either sabotaging or allowing it to be opened and destroyed. So it's a lot of fun. I think like it grew really quickly. Like it used very kind of simple algorithms under the hood, I think. We're going to look at how to use these same algorithms, but it engineered them in a way that it feels very interactive, and they definitely went on to train many different types of models as well, but the kind of fundamental piece of technology that they're using is a basic text generator. So we'll look at how that is done. Markov models, yeah. So Markov models are really, really quite beautiful algorithms, I find. They are like the simplest AI model. I often teach it when I teach music or sound or speech. But they definitely arise out of some of these other ideas. So a Markov model is basically a state-based model. It learns how likely states are to change. It's a discrete kind of state-based model. I'm using a lot of terms, sorry. So the idea is that you have a set of known states, which is a word I'm just going to define. Like for language, that could be all the different letters are states. So you have 27 different states. For music, it might be a chord or a particular note. Yeah, let's just start with those. And the idea is that you want to model what is the most likely thing to happen. So if I see the letter T, the most likely thing to happen after a T might be an H. And it might be that, out of every possible sentence ever written, the letter H happens 80% of the time. So a Markov model tries to encode that probability, and it defines how to, one, create this probabilistic space, but two, also like how to generate from it. And there are many things surrounding the term Markov. Like there's Markov property, Markov states, Markov chains, and all of these things kind of gel together. But the general idea is that you can use something like you can use what's called a Markov model in order to model any sequence that is discrete, such as text or music, things like this. So we're going to jump into two COLABs, which I did not create. And they're both, I'll copy the links to both of these in the Zoom chat, but they will also be updated on the website. So we're going to start with the CHAR RNN one. Some people say CHAR RNN. I always thought that sounded a little more strange to me, so I go with CHAR RNN. Up to you. This comes from a I'm not sharing my screen, sorry. Cool, so we're going to look at this notebook first, which I've shared on the Zoom chat and will be updated on the website as well. As I mentioned, I didn't create this. Luckily, there are many resources for this model that we're going to look at, CHAR RNN, and I found that this one was, to my eyes, something that we could jump into. There's a lot of code in here, and we're not meant to understand every line of code here, but I will explain how you could then make use of this notebook and use it for your purposes. So this notebook comes from this website here. It was a problem set for this course, which is neural network theory and applications. I should know which. Okay, this was a Princeton course in spring 2020. From Sebastian Sung. Okay, so this is the original notebook from them. And what this notebook does is it will train a generative text model and allow you to do what's called sampling from that generative text model, which just means generate letters, basically, one after another. So we're going to look at that process. So you'll want to make sure you're using the GPU, and if you're cloning from this notebook, then it will already have the GPU set up. And previously, we were using a neural network library called TensorFlow. This notebook uses the other major neural network library. People use primarily only these two. There are many others, but the bulk of people use either Torch or TensorFlow. And this is developed by Facebook, this library, Torch. Let's see, so these are just a lot of imports, and yeah, so I will go through some of the major steps here. This entire code cell is just to download a piece of text file, as well as set up how to crop data from a text file. So you don't need to know you don't need to know any of this code. The only important bit of this code is if your text file, if your text in which we're going to use to train a model on, if that text exists on the internet, you can reuse this line of code here and replace it with a text file that is on the internet. Alternatively, you can upload a text file and read that text file with Python. So we've seen in the second or third lecture how to write a text file. It was a very quick demonstration of that, so I wouldn't expect everyone to remember that, but if you want to read a text file, then you can do that in Python as well. Basically, what we need to train this model is a lot of text. So this variable represents that many characters. That's our entire data set that we're going to use to train this model. A lot simpler than images, right? Like we just have one variable that has all of our characters in a giant string. So you can create a text file using whatever editor that you'd like, and you could upload it here and read that into a Python variable. And that would be your data set. The text file itself needs to be a text file. Like it could be, some very different type of text. Like it could be HTML. It could be source code. It could be a lot of things, right? But it shouldn't be like a binary file, basically. It should be letters. The letters could be a lot of things, though. In the case of Ross Goodwin's Sunspring, it was text that looked like a screenplay, right? Like it had specific spaces to denote when there were major breaks in the scene. It formatted the text in a way that there were characters. So if we look at screenplays text, there's specific formatting for a screenplay. and it will look like this, right? And so there's a lot of cues inherent in just the structure of this text. There's specific spacing in between each part of the text. There's usage of caps lock or all capital letters in certain parts of the text. And those are all pieces of information, effectively, that the model can make use of. Where are we at? Yeah, so in this case, this is a Shakespeare play data set and just has loads and loads of Shakespeare in it. So it's going to have a structure that looks like a person, colon, and then the text that they're speaking one after another. Okay, so that's just a bit about the data for this particular model. Here we have the entire network definition. So this is a neural network in Python code in PyTorch. This particular model is generally what's known as car RNN. It has as input a letter, one letter at a time, and it projects that letter using some matrix math into a really high dimensional space. And then it builds what's called an RNN, hence the name car RNN. RNN stands for recursive neural network. Recurrent neural network, not recursive. That's a different network. Recurrent neural network. And the whole idea behind a recurrent neural network is it's just like a normal network that goes from input to some projection to an output, except you then take that output and you also feed it into the projection in the middle on the next time step. So there's this idea of time in a neural network for recurrent neural networks. And it's definitely beyond the scope, I think, of this course to try and detail it too much, but if you want to know more about the mechanics of that, I can definitely go over that. If there are no takers, then I will move on. Okay, moving on then. So this code block is just defining the definition of how to create this model called car RNN. You won't change it. You don't have to change it at all. Up until now, really the only part of this notebook that you would want to look at is how do you create this variable data? And here they created it by downloading a text file. You could have created it by uploading your own text file and then reading that with Python. Session 2, we have uploading files or mounting Google Drive. So these are two ways that you could get files into your notebook environment. The third way is you can hit this button here, upload. And that will also upload a file. So for instance, let's find some text files. I need a text file. Great, so this is a text file with one letter in it only, but there you go, there's a text file. And now it's in my environment. I would say if it is online, that's a lot easier because then it's just here in code. There's no like manual clicking of things. So you basically can just run the notebook if it's online. Whereas if it's on your desktop or wherever, you have to every time then upload it. There are ways of changing the way that you feed data to the same algorithm so that it can make use of that information. So just like we saw here, we're always going to have some bit of text that says who's speaking, and then the text, and then another bit of text that's who's speaking, and then the text. You could imagine changing every line of text in this so that it has the name of the book first before every line. And so in that way, the model always needs to know the name of the book before it says what happens after that, right? So there are a lot of tricks like that, where you're using the exact same algorithm, but you're changing the data that you give it, and it leads to really different behavior and capabilities. So we were looking at this, really not much to explore here except for maybe this parameter and the number of layers. So when the model is created here, it will pass in different parameters for these variables. So you can set the cell to Lstm or RNN. Those are the two options. The Lstm is another type of recurrent neural network. It uses a much more complex type of cell that allows it to understand longer sequences much better. So the RNN's capacity for retaining what it has seen previously and working that into what it will then generate, it's theoretically it's infinite, but practically it's actually just really quite short. And so it has this forgetting problem. Like it'll just forget where it was and then start just spewing like whatever, you know. The Lstm goes another step farther, and its capacity for remembering things and working in memory from previous states into the current state is better, a lot better than the RNN. And the model that we're going to look at after this is the state of the art for memory. Like the Lstm will, the RNN might remember 20 letters ago, the Lstm might remember 100 letters ago, and the GPT, which is what we're going to look at after this, that model will remember like pages, basically. So if your sequences, the data of text that you're feeding in, if those have patterns that you want the model to remember over a longer time period, then use the Lstm. The number of layers and the hidden size are controlling the size of this network. So the number of layers are, in a network, there are many projections. You go from your input to the first hidden layer, and that's one layer, and then to the output. That'll be a one-layer network. If you go from your input, which is the character, to this first layer, and then you go to another layer, you're allowing your model to learn more intricate dynamics and try to reason more about what's happening. It's more challenging in terms of the amount of time it takes to compute, in terms of how much memory it takes to compute that model, in terms of how much data you need in order for it to figure out all of these things. So they're all of those things kind of interplay with the number of layers. For this model, you generally want 1 megabyte of text data in order to train something like a 3-layer neural network. If you have much less data, try smaller layers. And generally, the rule is like scale up. Don't necessarily scale down. Like, start with a simple thing and then add complexity. So see where you get with like a 1-layer RNN with 100 neurons if your text size is 0.5 MB. And then as you add more data, scale it up. Go up to 2-layer Lstm, go up to maximum size for a hidden size is 1024. This is the type of network that Ross will have used for Sunspring, for One the Road, the type of network that S uses for poem portraits. And that is the architecture. Maybe it's 3, but you probably can't even tell the difference between 2 and 3. Okay, so keep this back to the smaller network. Learning rate, you don't have to touch. The number of epochs is how long is the model going to train. So in Runway, you saw number of iterations. That is the same parameter here, number of epochs. It is how many times will it see your entire data set. This other stuff you don't have to worry about unless you're running out of memory. If you're running out of memory, you might remember from second or third, when we were using Inception to project our data, you might have remembered that we were running out of memory certain times. You can make the batch size smaller and you're less likely to run out of memory, but the model won't have trained as well. So you probably are fine with 100. There's plenty of memory, luckily, for this size model. You'll probably start to hurt if you are using a 2-layer 1024 hidden size network. Maybe that will fit on COLAB. Drop this to 512 otherwise, and keep the batch size 100. Okay. So you more or less can just use the script as is. We can continue executing code. I forgot to execute this one. So I'm executing each cell. I'm not changing anything. I've just told you a bit about how you might change these, as well as these parameters. You don't really have to change these. This is the function definition for training. Don't have to change it. Another function definition, don't have to change it. All looks good. And then here is the actual training bit. This is just going to show you what's happening during the training a little bit. It's going to show you a progress bar, show you how far into the 2000 epochs you are, as well as show you the loss parameter, which is just a number that should be close to 1. Like if your loss is up in the hundreds, then the model really doesn't know what it's doing with your data, and you might want to figure out why that is. It's probably too chaotic, or there's not enough structure, or there could be ways that you could introduce more structure to your text data. Also, you will see generations from the model, as in like randomly, the model will just have been in a state, and it will say, like, what's the most likely next state? And it'll be a W. And then, okay, great. What's the next state after that? H. Okay. And then just keep going 1 letter at a time. And it ends up spitting out this entire sentence. And it'll just keep doing that at each training step. And it will just show you, kind of where the model is. And you'll start to see very early on something that looks more like Jabberwocky, and it will have lots of round letters if you're using an English language text corpus, and it will kind of be round kind of sounds. For some reason, it learns consonants later more. Just something I've seen. And in this case, it's Shakespeare, so it's kind of also got the intonation or rhythm to it as well. So that's the training. This is the part that takes a long time. For this Shakespeare text file, you can see it took about 20 minutes estimated to train that text file. At the end of it, you will have a variable decoder here. Is that right? Let me just make sure. Yes, the decoder is the variable that is this model that was created up here. And you can see that it's generating here inside of the code, and it's feeding it a seed text of WH. And that's why every line here starts with WH, WH. The number 100 here, I believe, is how many samples to take following that WH. It will then print out another 100 characters, basically. So following the end of this training, you can give it a different letter to start with, or whole sets of letters to start with, or many sentences to start with. And you can also give it this other parameter, temperature. So I mentioned that this temperature parameter stems from thermodynamics and comes up in this model. It will basically affect how chaotic the probabilities are on this model. So with a higher temperature, I hope I got this right. I always invert these, but I'm pretty sure that with a higher temperature, you're adding more chaos into the system, and so there will be a lot more uncertainty. And what happens is that you're basically rescaling the probabilities of this space that it's in. So instead of seeing A and D, most of the time, if you up the temperature, it might really jump it into another state that was less likely without that high temperature. But because you're adding lots of heat to the system, that's the idea. Pretty sure I have that the right way. And then the opposite of that is if you make the system really cold, you are basically going to be very, very deterministic. You are telling the system that, you know, whatever your most probabilistic outcome is, like you should really just do that. Don't add in any uncertainty to your system. Just use the most likely thing. That's it. So you can get really different behaviors depending on what you've trained on and what you seed it in terms of this prime string here. This just means like the seed text, it'll be called in other places. And then this temperature parameter. And that's it. That is the CAR RNN model. And there's loads and loads of other examples online that you could find, but this has all the basic functionality of a CAR RNN model, and I found was quite easy to use in COLAB. I would try values between 0.5 up to 2, and beyond that probably won't make a huge amount of difference. I would stay around 1 you know, like some models have good behavior around 0.8. Like just try between 0.5 to 1.5 in increments of 0.1 and try a lot of generations and try to build an intuition for what your model behaves like. They're all quite different somehow. So I'm not doing a live training of this one because I'm not going to wait 20 minutes for it, but trust me that it works and that this is the output for that particular model. So yeah, the next type of model that I want to show you is the GPT-2 model from OpenAI. And this is one of the most state-of-the-art models that you can actually use as open source. And something happened between car-RNN and GPT's kind of scale. Like this is a 1 megabyte scale. Like we're talking about quite a small model. It has one layer and 100 neurons in it. There's a bit more for the recurrent connection, but you know, the size of this network is really tiny and can still generate, you know, Shakespeare. Like, you know, it's not great or anything, but GPT-2, on the other hand, is hundreds of megabytes of parameters. And the order of that allowed it to consume a lot more information. And the researchers that worked on that in OpenAI, as well as other companies like Google, Facebook, Microsoft, NVIDIA, all these companies are getting increasingly better and more capable at ingesting more data and computing on it faster. And at the same time, they're also getting more data. So it's like this never-ending cycle of like, where is it going? How much can it learn and how fast can it learn? How big can the models be? And yeah, it's just it's a trajectory that, you know, is staring us in the face, and it's like, well, where does it go? So yeah, I'm very, very interested in what everyone thinks that direction will be, and yeah, I hope that we'll have more dialogues on it through the works that you create or just in this class. The other notebook that I've found that I think is very useful for learning GPT is this one by Max Wolf. You don't have to use this to train GPT. It's just that this is free, so that's nice. You can train a GPT-2 model on Runway, but then you'll have to use credits, and I'm not totally sure how many more credits that we have. So I wanted to give you this option in COLAB as well. But if you want to train a model in Runway for GPT-2, it's really straightforward. You will go to train and then hit generative text, call it whatever. Then you can upload a data set, which is just uploading a text file. You can upload a whole folder of text files or multiple files of text, or you know, however you can get text, you can upload it. So I don't have any text files. Why not? well, I need some text files. I'm just going to make a text file. Let's go here. Text file. My text file. Okay. There's my text file. And then I should be able to open this with Runway. And that will be my data set. Okay. It's got a recommendation that it should be bigger than 100 kilobytes. And in general, it should be about a megabyte, really. So it won't even let me train that, but you know, there are some examples here. If you eventually upload your data with Runway, then you will see a preview of your data set here, and you can hit next. There will be different options for the size of the model, as well as what you can prompt to the model to see during training. Just like we saw with car RNN, we were prompting during training the letter WH only. So here it's prompting this whole phrase. In terms of the size of the model, that really depends on, well, it depends on how much data you have first. Like, do you have a megabyte of data or do you have like hundreds of megabytes of data? If you only have a megabyte of data, you're probably okay with the extra small or small models. What these are existing trained models by OpenAI that are capable of generating text very well, and they have been trained on the internet. They've been trained on Reddit and various sources like that that have been cleaned up and filtered and in certain ways, but they are generally just full of every topic. They're pretty insane. So there was a website called Talk to Transformer. Right with Transformer, okay. So this is the model, GPT-2, and you can see what happens with this model live with this interface. This is the large model here. So you can switch to the extra small or small model here and see what it would look like already. That would correspond to these three. They don't offer the large or extra large models training. But I'll put this in the chat. So, okay. What does it mean to prompt text? Yeah, so prompt text is this bit of text right here. It's also known as the seed text, or what this calls the prime text. All the same thing. It's basically, what do I give to the model before I ask it what is the next thing that it thinks about? Is that clear? I know it's really abstract, but basically it is the text that you're going to give the model before you ask it to continue generating. So the seed text would be whatever I write here, you know, like Shakespeare is, and then this model will go and generate when I hit tab, and it'll give me different generations. There you go. It's a great example of that. So this is the same idea as CAR-RNN, except it's just like many orders of magnitude larger of a model, and it's been trained on way more data, as in the internet. I believe it uses a data set called Common Crawl, which is a nonprofit that continually downloads the entire internet. And it just has like all the data of the internet. There's every month cataloged. It's got about 60 terabytes of data. I believe GPT-2 did a lot on top of this data set, and it's definitely a much smaller subset of that. It's constrained to text as well. And I don't know the character set of GPT-2. I feel like I should know that. That is something that I'm curious about now. Maybe talk to Transformer can answer us that. Let's try some Chinese letters. I need to search for one. Let's do this. Okay. I don't know what I'm looking at, but Jen, do you want to step in here? Does this seem like a sensible completion? The fact that it has this letter here makes me think that it does know other than English vocabulary letters. And I just don't know how good it is at those things. Maybe the larger model is better, but have a play with that. Let me know if you find, I put this on the Zoom chat, let me know if it works for you in any capacity. I'd be curious to know. And then in terms of Runway supporting those letters, I don't know, but if it doesn't, I'm sure that's something that Cristobal, the creator of Runway, could help with, and we could ask him, like what, can you push a version by tomorrow that supports this character set, please? And then we'll hope that he's willing to do such a thing. But it is, as we saw with CAR-RNN, generally a one-line change is just with Chinese. I'm not totally sure what the one line should be. So we'll look into that. Cool. So back to training with GPT-2, you have fairly similar options. With training the StyleGAN model, you also have this number of steps that you can use. You have this option to convert all of the data and the generation of the model to lowercase, which makes me think that it's really kind of English-based, this interface for this model. I don't know. But basically what it's saying is that, do you want your model to only know lowercase letters? And the reason why you might do that is that if there are less possible states, so if I have 27 lowercase and 27 uppercase letters for the English language, then I have twice as many possible things to know about, versus if I have just lowercase, then my world is a lot smaller, and I don't care about the difference between uppercase and lowercase letters. So it can be a good thing or a bad thing depending on what it is you want to do. If if your data set has information and structure that only uppercase letters allow the model to learn about, such as in a screenplay, you always have all the character names or the transitions between scenes on all uppercase, like that's really useful information. If you convert it to lowercase, it won't know to associate those things. Yeah, and then they have this option for dataset preprocessing as a separator. This, I think, is related to Connor's question. So there are different ways of feeding in data in Runway, and they give you some guidance on each of these. The car RNN approach is basically the last bullet point here. So if you just have a continuous stream of text and there's no distinction between files, the line separator is more akin to a quote generator, so you don't care about the association between lines. You just care that one line has all the information that it needs to generate something. And then there's what are these options? Sorry, the paragraph or the document models. They give you some indication here, like if you don't care about the associations between each paragraph, then go for the paragraph model. Whereas if you care about what's happening between paragraphs, then go for the document approach. And that's pretty much it for training options. When you have a model, you can generate from it by giving it text. So this is the checkpoint that I trained earlier on one of their sample data sets was Lord of the Ring. And you can prompt it text. So you can write seed text, prompt text, all the same thing again here, and it will continue to generate past that point. Or you can give it a text file and it will read that as instead. It's the same thing as like pasting that text file here. The parameters that you have over here are, so how many letters should it generate following what you've given it? So if I say, like hello, space, then how many letters after that should it generate? Top P is a way of sampling the model. It will allow more likely things to happen or less likely things to happen. So it's related to this temperature parameter, but it's not quite the same. But generally, the same type of control. So if it's quite high, then you're only allowing things that are really, really likely to have occurred in your data set. You're only allowing those things to happen. If you set this to be really low, things that weren't in your data set, they could also happen with much greater probability. So it's much more chaotic in this way. So I think that's inverted from the temperature parameter. And then seed is just a parameter that allows you to get reproducible random behavior. So if I change the seed, then I will get a different random behavior. If I change it again, I'll get a totally different random behavior with the same text here and all the same checkpoint, everything being the same. I will get different output. Yeah, that's the whole gist of it, really. So within Runway, you don't get like programming capabilities, so you would have to pipe the output of this to something else, or export it and then do that analysis somewhere else. So you can export a lot of different outputs. Like you can ask for 1,000 different examples of outputs, and then use this input text, or just a random kind of input if you select none. And then that will save all the files as text, all the different generations, these 1,000 different generations, which you could then load into a program like Python to do that analysis. So that's how I would approach it. Either using Runway to generate the text and export it and then load it into something like Python. That's where I'm comfortable. Or do the training. If you're using RNN, then you'll have the text as a string in Python already. In terms of the libraries, like if you were comfortable with using Python, the libraries that you could use to do that, there are a few I could recommend. NLTK is one. Spacey is another. And both of these will allow you to do like quite advanced things with language. Like if you wanted to count all the nouns in the generated text, or just count the verbs. It can do parts of speech tagging. It can detect when there's a named entity. Those sort of things will allow you to do some other additional processing on the generated text. You could also just use straight up Python and like split on the strings spaces, and that would give you a list of different words that you could then count. A couple approaches there. So I think that's it for Runway. So this is the last bit of GPT stuff that I wanted to show you, and it's a COLAB that allows you to train a GPT-2 model and generate from it, all in COLAB. So it's pretty code heavy again. The library that it's using is really meant to be used with COLAB because it has like functions to save a checkpoint into your mounted Google Drive on COLAB, and like it really tries to make the process of using GPT-2 in COLAB simpler. It's not like something I can train in a couple minutes, but I will walk through the steps just to kind of show you that it works. This is installing the library that it's going to be using. Again, this is from Max Wolf. And there's also a blog post where he describes it. And it's quite good. I've used it in projects before and given it to people as well. And they seem to have been able to use it still. So there's always a chance that this library will stop working at some point, but for now it's working. And again, you'll want to be using a GPU runtime, which if you clone this, it will be. And this is just confirming it. Like this is a command that will talk to the operating system and tell you if there's a GPU or not. And you can see there's a Tesla GPU with 16 gig of RAM here, which is amazing. Let's see. So just like with Runway, you get the option of which model to train. These are all pre-trained models from OpenAI that were trained on Reddit and whatnot. And in COLAB, you're limited by the amount of memory you have. So there's advice here basically saying that you can basically pick the small or the medium model. In Runway, they had an additional model, the extra small model, which is I believe, a distilled version of the small model, which is basically a way of training a model from a model. And that allows it to be a lot smaller. So if you want to train the medium model, you'll basically replace this string with 355M, and that will train the medium model. If you've got a Python environment set up and a GPU and you've got much more memory, then you could potentially even train the large model by changing that line of code. And if you really have a lot of memory, the 1558 model, but I believe that requires like 32 GPUs and like a month training or something ridiculous like that. So yeah, so we'll stick with the default small model, which is still massive. I mean, the next thing it will do is mount Google Drive. So that will ask for your authorization code to mount it. And the reason it's asking for this is so that it can save the checkpoints on Google Drive, which means that when you come back to this after it's been training, you'll actually have that model saved already and you don't have to retrain it. Really useful. So I will give it access to my Google Drive. Copy the OAuth code. Oh no, how did I do that? And then paste it. So it should appear here. I just refreshed it here with this button. And I'm seeing my drive now listed here. Just like in the car RNN notebook, you can download a text file or upload one, but at the end of the day, you will need a text file. And here it's going to just keep a copy of that text file in the drive. Well, wherever you keep it, you have to know the file name of the file that you're going to train on. And so that is the one variable here that is being used here, the file name. You'll need to change the file name to whatever, if you download a file or if you upload a file, it has to be the name of that file. Okay. So we download Shakespeare. We now have a file called shakespeare.txt. That file was then copied to the drive. And so it will be inside the drive here. And then this file name is going to be given to this function, Shakespeare.txt, and it's going to say, look for this file in my drive. So not this one, the one that's in my drive, and then copy it. So this is the line of code that will tell GPT-2 what do I train my model on. Next, it will train the model, and it's called fine-tuning because there's already a model that's been trained by OpenAI, and it's just continuing the training process. That's what's called fine-tuning. So this model was trained for however many steps. Maybe it was like 100,000 steps. And when we go and hit fine-tune here, we're going to be on the 101,000th step. Except now it will be your data instead of OpenAI's data that it sees. It's going to be like, whoa, what just happened? It'll be very different data, but then it will learn how to generate text that looks more like that new data. The defaults here are quite good. Like this is the same parameter as the steps parameter in Runway, or the number of epochs for the car RNN model here. Same parameter. And you can tell it to print its loss here, like the statistics of how well it's training every so often, and when to generate some new samples. After this is done, you can then save the model. So definitely do that. Make sure you save the model if you don't want to repeat the whole process. It will write the model to a folder called checkpoint. So let's try this and run it. And each time you start a new training process, it will create a new folder inside of checkpoint. So starting with the first time that you run it, it will be called run 1. The next time you run it, it will be called run 2, and so on and so on. And so you get basically a history of every time that you computed this model and asked it to retrain. So the first time I run it, I get a folder called run 1, and there's a lot of files in here that are everything that the model needs to pick up from where it was and generate text. So it's going to save after 500 steps. It's currently on the 10th step or so, but after 500 steps, it will save a new set of files here. And so if I don't want to wait for 1,000 steps, I want to stop after the 500th step, I can do that. And I will have everything I need to get the model back to where it was. So, I mean, we don't set save every to 1 because then it would just be a lot slower. So we just save every so often. Once you're done training, then you can go ahead and copy these files to your Google Drive. And so that way, if you restart this whole notebook and you come back tomorrow, you can just call this line of code copy checkpoint from drive, and that will load that same checkpoint. And you won't have to compute the fine tuning or copy the checkpoint. You'll just have to initialize GPT-2 here. So you would have to run this cell of code and then skip all this stuff. Mount the drive. So you will still have to mount the drive. So you would import this stuff. Don't need this. Don't need this. Actually, you do need this. Apologies. No, only if you're retraining the model. Okay, because we're going to have the new model. Sorry. So you will have to just import this stuff, and then you don't need to download. You don't need to. Yes, you need to mount in order to get your version of the GPT-2. You don't need to download your data set. You don't need to copy that data set to the drive. You don't need to fine tune, and you don't need to copy it to the drive. You just have to copy that checkpoint back from the drive. And then this will load up the model, and then you can generate from the model. So this function has a lot of parameters. It has that same temperature parameter, how long to generate for, and what to seed the model with, as well as how many different samples should it provide. You can also do the same thing, but generate it to a file. Yeah, this is if you want to generate from the base model, not the one that you've trained. And that will let you generate with the larger models. So this is sort of like using this interface, but now you get it in code here. So you can actually just generate it with this code. And there's more control here in code. But that's it in terms of GPT-2. Are there any questions on this? This is the wrong title. So car RNN, there's no pre-training. It's a very small model, and there wasn't like the internet of data being fed into it. And it's, it requires very little data. It's a very small model versus GPT-2 is hundreds of megabytes of size. Like it was trained on the internet. It was trained on like a lot of text. So it was like a massive model. It knows a lot of things, as in like you can talk to it about things. Like, how's it going today? And then this is just generated, totally generated. It's pretty good, yeah. Okay, cool. Bye. You can't do that with car RNN unless you've given it specifically data about conversations like this, right? Whereas this is GPT-2 has seen like conversations like this on Reddit or wherever, and it just, it's giving you the most likely thing that could have happened based on what it's seen before. Yeah, GPT-2 is quite obscure. Like if you try to find its pockets, like, like really how much of the internet did it learn, like does it know about that subreddit, or does it know about that weird part of the corner of the internet over there, and like just try and find what it knows. Like it goes places. It's, especially the large model, is very, very strange. So I'd like you to train a model. You can train it in Runway or in COLAB. If you use COLAB, you have two examples that I've given you for car RNN or GPT-2. With that generative model that you've trained, I want you to explore 10 different types of seed texts. So this is pretty relaxed. I mean, we've seen what a seed text could be. Like it can be as simple as a letter. It could be an entire word. It can be an entire sentence. You can really explore here. But this is really just to get you thinking about where these ideas could extend into a more polished piece. And then the last bit is really just an optional exercise for you, not required. There are two other types of generative text models, and I've linked those here in this PDF that will be shared on the website or is already shared. And that will link to two different models that you can actually use in COLAB. And you can't train these models easily, but you can use them as is, and they offer really different types of control. So they're not just generative text with seed text, they are really quite interesting in the axes and parameters that they provide. So that's it.